Hey guys, welcome back. Sorry I couldn't make it today, but let's try it this way. Alright, so we're going to pick up where we left off with logarithms, and we're going to solve some logarithms today. So here's our first example. We've got log base 2 of the quantity x plus 2 added to log base 2 of the quantity 5, and that equals 4. Alright, so what we want to do is we want to get x by itself. Right now the x is in the logarithm, so we're going to have to take and combine the logarithms. We know that we've got the addition, we can take and multiply, so this goes to log base 2 of 5 times x plus 2, and that equals to 4. We now know that if we slide the base, then we get the x term isolated. So I have 5x plus 10 equals 2 to the 4th. 2 to the 4th is 16. That's equal to 5x plus 10. So 6 is equal to 5x, and x equals 6/5. Next example, got the log base 6, the quantity of x plus 1. That again is added to log base 6 of x, and that's equal to 1. Alright, so once again we've got the addition, so we go to a multiplication. So this is the log base 6 of the quantity of x times x plus 1 is equal to 1. Slide the base, get 6 to the 1st is equal to x squared plus x. So now we've got a quadratic set aside equal to 0. Factor. 3's got to be positive, 2's got to be negative. And we end up with a value of 2 and negative 3. This guy, negative 3 is extraneous because when I plug it back in, log base 6 of a negative number, what power of 6 is a negative number? Doesn't work. So the 3 is going to be extraneous. So 2 is just our answer in this case. Alright, let's do one more kind of similar to these. We've got the log base 4 of the quantity of 2x plus 1 subtracted by log base 4 of quantity of x minus 2, and that's going to equal 1. Now, instead of addition, we have a subtraction separating the two, so that simplifies to a division. So I have the log base 4 of 2x plus 1 over x minus 2. That equals 1. Slide the base again. 4 to the 1st is equal to 2x plus 1 times x minus 2. Multiply by x minus 2 to both sides gives me 4x minus 8 is equal to 2x plus 1. 2x equals 9. Therefore, 9/2 is equal to x. Alright, now, a while back we talked about solving a problem to this. 5 to what power is equal to 7? I have no clue. Alright, but what we found out is that if we slid the base, then we could write this like x equals log base 5 of 7. That's its logarithmic equivalent. Alright, but our calculator won't do this. Alright, and we could probably graph this and find out what value x is going to be, but we're not going to. Okay, luckily algebra now has some properties that we're able to use for logarithms. Alright, Whatever I do to one side, I can do to the other. So what I'm going to do is I'm going to take the log, common log, log base 10, of 5 to the x. And if I do it to one side, I have to do it to the other side. So log base 10 of 7. Now, by that third property on your logarithms that we covered before Christmas, we can bring the x forward. So x log 5 is equal to log of 7. And therefore, isolating x, I get x is equal to log base 7 over log of 5. I think I said base 7, but it's just log base 10 of 7 is over the log base 10 of 5. Now notice, this x is the same as this x. So it must be true, then, that log of 7 over log of 5 is equal to log base 5 of 7. And it is. Now, here's the deal. I can find the log base 10 of 7 on my calculator, and I can find the log base 10 of 5 on my calculator. So I can actually calculate what the log base 5 of 7 is equal to. And that's going to approximately be 1.2-ish. All right. Now, this is the approximate answer because there's a load of decimals with it. This is the exact value here. All right. Now, this new idea right here brings about the concept called the change of base. And what the change of base says, it says if I have any log base p of q term, that's equivalent to the log of any base, I'm going to call it b, of q over the log of that same any base, call it b again, of p. So that allows us to basically approximate any logarithm value. For instance, if I have the log base 27 of 50, and I want to find its exact value or rewrite it using a change of base, I can say that's equal to the log of 50 over the log of 27. And then I can just pop that into the calculator again and roughly get 1.19-ish. All right, so now we're ready to solve some tougher problems. We can now solve for terms with an unknown power. In other words, for a problem like this, 3 to the x plus 1 is equal to 84.2. There would be no way I could get the same base here and then set the powers equal, but now I know all I have to do is take the common logarithm of both sides, like so. I can bring that power out in front, so that's the quantity of x plus 1 times the log of 3 is equal to the log of 84.2. Now if I wanted to put this, give this the exact value, then I'd take and divide by the log of 3, so I have x plus 1 is equal to the log of 84.2 over the log of 3, and then subtract 1, so I get the log of 84.2 over the log of 3 minus 1. And then if I wanted the approximate value, I could take and pop all that in my calculator. Move to another example. Let's take the following. Say I have 4 times 2 to the x plus 5 plus 12 is equal to 44. Now the big mistake here is people will multiply 4 times the 2. No go. You want to bring the 12 over first. Get a 36. It's equal to 4 times 2 to the x plus 5. Keep in mind that if you did want to multiply those together, you have to have the same base. All right, now I'm going to divide by the 4, which gives me a 9 is equal to 2 to the x plus 5. Now we're back to the same problem we just had. Take the log of both sides. Bring the x plus 5 out in front. Divide by the log of 2 and subtract 5. So I've got log base 9, or sorry, the log base 10 of 9, or the log base 10 of 2 minus 5 is equal to x. And then we're done. Alright, so let's jump to, we've got 2 more examples. Let's jump to a tougher one. 7 raised to the x plus 5 is equal to 2 to the x. So this is different in the case that I have unknown powers on both sides. Well, again, I want to get these unknown powers out in front. So I'm going to take the log of both sides. Then bring the powers out in front. Now this is a little different because I've got an x times log 2, which means I can't really separate those. I'm going to take and distribute this through. So I have x log 7 plus 5 log 7 is equal to x log 2. When we did beginning algebra, we tried to get all the x's to one side, all the numbers to the other, so that we can isolate the x. So I'm going to do the same thing here. I have x log 7 minus x log 2 is equal to negative 5 log 7. Factor out an x over here. Get log 7 minus log 2. That's equal to negative 5 log 7. And then I just take and divide. So x equals to negative 5 log 7 over log 7 minus log 2. Last example. Say I have 3 e to the 4x minus 5, and that's equal to 33. First step, get rid of the 3. So 11 is equal to e to the 4x minus 5. Now, since the base is e, I'm going to use a log of a different base on both sides. I'm going to use the natural log, and I'll show you why in a second. Anytime I have an e in my problem, I'm going to use a natural log. So I bring the 4x minus 5 out in front. It's a natural log of e. And that's natural log of 11. Now, natural log of e, let's go over here, says basically this is the log base e of e. So what power of e is e? 1. This whole term goes to 1. So I have 4x minus 5 is equal to the natural log of 11. Therefore, the natural log of 11 plus 5 over 4 would equal x. And that's all we got for today. Hopefully we'll see you tomorrow.